Today, I'm going to be talking about Chapter 4.3, Derivatives and Graphs. So first, to review some basic information, if the first derivative of a function is equal to 0, then that function is constant. If it is greater than 0, then that function is increasing, and if it's less than 0, then that function is decreasing. So today I'm going to show you how to find the critical numbers, areas of increasing and decreasing, local maximums and minimums, concavity, and points of inflection of a function using its derivatives. One way is to use the first derivative test. The first derivative test basically says that if the first derivative goes from negative to positive, there's a local minimum. If it goes from positive to negative, there's a local maximum. And if the sign stays the same, then there's no local maximum or minimum. Here's two graphs that explain that. See, if the first derivative goes from positive to negative, that means the function itself is going from increasing to decreasing. Here you can easily see that at the top there would be a local maximum. If the derivative goes from negative to positive, then the function itself goes from decreasing to increasing, and here would be the curve, and the local minimum is at the bottom. So here's our example. Here's our function, and first what we want to do is find the derivative. After we find the derivative, we set it equal to 0 in order to find the critical numbers, which in this case are -1 and 1/2. Then, with these critical numbers, we want to create a table. With this table, we'll be able to see the first derivative where it's positive and negative, and therefore where the function is increasing and decreasing. Here are two critical numbers, and here are just some numbers, x values, to plug in. We find these answers and therefore can say that f of x is increasing from -infinity to -1 and 1/2 to infinity, and is decreasing from -1 to 1/2. There's a local maximum at -1, 6 and a local minimum at 1/2, -3/4, because at -1 there's a sign change in the first derivative. It goes from positive to negative. There's a local minimum at 1/2 because there's another sign change at 1/2 where it goes from negative to positive. Then we find these two y values by plugging in the two x values or critical numbers into the original function. We can also use the second derivative test to find the local extrema. So the second derivative says that if the first derivative is equal to 0 and the second derivative is positive, then the relative minimum is at c, f of c, which just means that at this point there's a flat spot and the rest is concave up, or the function is concave up. If the first derivative is 0 and the second derivative is negative, then there's a relative max at c, f of c, which means there's a flat spot that is concave down. So using the same example, we can see that the critical numbers of the first derivative are still -1 and 1/2. Then we can find the second derivative, which is 24x plus 6, and plug in these x values. We find that f of x has a relative max at -1 and a relative min at 1/2, which is the same values that we got by using the first derivative test, which is perfect. Next, I want to talk about concavity and points of inflection. There's 4 different types of concaves. There's concave down, increasing, concave up, increasing, concave down, decreasing, and concave up, decreasing. They're all shown here. Points of inflection, or POI, are where the concavity of a function change. So, for example, right here on this function. In order to find the point of inflection is finding where f double prime of x changes signs from positive to negative or from negative to positive. You can also do this by finding where f prime of x changes from increasing to decreasing or vice versa, because f double prime of x is just the derivative of f prime of x. So using the same example from before, we can find the concavity of the function and its point of inflection, or points. So first we get the second derivative of the function, which is 24x plus 6. Then we find the critical numbers, which in this case are, or is, negative 1/4. Then we create another table. Now, negative 1/4 is our critical number, and here are just some values that we're using to input, as input. Then we find this information. As the second derivative of f of x is negative, that means the first derivative is decreasing and the function itself is concave down. If it's positive, then the first derivative is increasing and the function itself is concave up. So here's the shown the domain. And then in order to find the point of inflection, as I said earlier, it's the change in sign of the second derivative. So from negative to positive, we know that there's a point of inflection there. We can also see that there's a change in the first derivative from decreasing to increasing, and we can also tell that in the function itself, because it's changing from concave down to concave up, we know there's going to be a point of inflection. It's at x is equal to negative 1/4. Thank you.